Hello there, and welcome to Sleepy Science. Tonight, we're exploring sand, and you're surrounded by it right now. It's in your walls, your windows, the glass you drink from, the screen you're looking at. Sand built the world you live in, but here's what makes it truly extraordinary. Every single grain carries a story millions of years old. Mountains became pebbles. Pebbles became sand. And that journey, from peak to shore, is one of the most beautiful tales on Earth. So find your most comfortable position, let the day fall away. And if you enjoy these quiet journeys into science, tap that like button and subscribe so you don't miss tomorrow's story. Leave a comment too. Tell us where you're watching from and what time it is there. We love knowing our community spans the whole world. Now, let's begin with something small that holds something impossibly large. Pick up a grain of sand, just one. It sits in your palm, barely visible, weighing almost nothing. But that tiny speck is a time traveler. It's older than cities, older than civilizations, older than humans entirely. That single grain might have started its life as part of a mountain peak, touching the sky, sharp and proud. Then weather arrived. Rain fell. Ice formed. The mountain cracked, just a little. Then a little more. Over thousands of years, that peak broke apart. Huge boulders tumbled down slopes, crashing into valleys below. They shattered into smaller rocks. Those rocks rolled in rivers, grinding against each other season after season. Sharp edges wore smooth. Big pieces became small pieces. Small pieces became smaller still. The mountain was forgetting its shape, transforming into something new. Your grain of sand was born somewhere in that long breaking. Maybe it split from a boulder during a particularly cold winter when ice wedged into a crack. Maybe it chipped off while tumbling down a riverbed for the 1,000th time. However it happened, it became separate, individual, free to begin its own journey. And what a journey it was. That grain might have rested in a riverbank while dinosaurs walked past. It could have been buried under ice during an ice age, frozen in darkness for 10,000 years. It might have blown across ancient plains when mammoths roamed. Human civilizations rose and fell, while that grain moved slowly, patiently, toward the sea. Every grain carries this epic inside it. Beach sand from California might have started in the Rocky Mountains hundreds of miles away. Desert sand in the Sahara could have once been part of mountains that don't even exist anymore. The white sand beaches of Florida are made from ancient sea creatures, their shells and skeletons ground down over millions of years into powder so fine it feels like silk. Scientists can actually read these stories. They look at sand grains under microscopes and see the history written in scratches, in smoothness, in color and shape. A grain with sharp edges is young. It hasn't traveled far, but a grain worn perfectly round has been on a journey lasting ages. The more polished and smooth, the longer the trip. This means something beautiful. It means the beach you walked on last summer is a library of ancient tales. Every step you took was across millions of years of history. Those grains between your toes witnessed worlds you can't imagine. They survived everything Earth could throw at them. And now they rest there, warm in the sun, waiting quietly for the next chapter of their endless story. sand doesn't rush. It moves at the pace of geology, which is the pace of patience itself. So how many of these ancient travelers actually exist? How many grains of sand are on Earth? The answer is a number so big it breaks your brain a little. Scientists estimate there are roughly 7 quintillion, 500 quadrillion grains of sand on our planet. That's a 7 with 18 zeros after it. Try to picture that. You can't. Nobody can. Our minds aren't built for numbers that huge. But here's where it gets interesting. For years, people said there are more stars in the universe than grains of sand on Earth. It sounds right. Space is infinite. Sand is just beaches. But they were wrong. Dead wrong. There are actually more grains of sand on Earth than stars in the entire observable universe. The universe contains about 70 sextillion stars. That's 70 billion trillion. It's massive. But sand wins. Sand outnumbers the stars. Think about that. Every beach, every desert, every handful of Earth contains more stories than there are suns burning in space. Let's make this even more personal. A handful of sand contains roughly 10,000 grains. Cup your hands right now like you're holding some. In that small space, you could hold 10,000 ancient tales. That's more stories than you could read in a lifetime. More history than any library contains. And it fits in your palm. One bucket of sand from the beach holds about 12 million grains. 12 million separate pieces, each with its own journey. A single beach might contain more grains than there are humans who have ever lived. Walk across any shore and you're stepping on a population larger than all of human history combined. The Sahara Desert alone contains enough sand to bury the entire United States under 30 feet. Every dune, every ripple, every wind-carved pattern is made of more grains than your mind can count. You could spend your entire life counting just one small dune and never finish. But numbers this big actually teach us something beautiful. They teach us about abundance, about how nature doesn't do anything small. When Earth makes sand, it makes oceans of it, mountains of it. It creates with a generosity that seems almost wasteful. But it's not waste, it's abundance. It's the universe showing us that some things are meant to be infinite. This abundance also reminds us how small we are, not in a bad way, in a peaceful way. Your problems, your worries, your struggles, they're real and they matter. But set against 7 quintillion grains of sand, against geological time measured in millions of years, there's a strange comfort. You're part of something so vast that your troubles become just one grain on an endless beach. The mathematician Archimedes thought about this over 2,000 years ago. He tried to calculate how many grains of sand would fill the entire universe. He came up with a number, though he didn't have the tools we have now. But he understood something important. He understood that even infinite-seeming things can be counted, can be understood, can be held in the mind if you approach them the right way. Every grain matters because it's unique, but every grain is also part of something too large to fully grasp. You are like that too, individual and important, but also part of a human story so big, so old, so ongoing, that no single person can see all of it. There's peace in that. in being one grain among quintillions, in mattering while also being part of something that matters more. But sand isn't just abundant, it's also surprisingly creative. Close your eyes and picture a beach. You probably see tan or beige sand, the color most of us know. But Earth paints its shores in colors you wouldn't believe. There are beaches out there that look like they belong on alien planets, and each color tells its own story. Take Iceland's black sand beaches. The sand there isn't worn down mountain rock, it's volcanic glass. When lava hits cold ocean water, it explodes into millions of pieces. Those pieces cool instantly, turning into black sand that shimmers like crushed obsidian. Stand on Reynisfjara beach and you're walking on frozen fire. Every grain was once liquid rock, hot enough to melt steel. Now it's cool beneath your feet, smooth and dark. Then there's pink sand. Bermuda has some of the most famous pink beaches in the world. That color comes from tiny organisms called foraminifera. They're single-celled creatures with red shells. When they die, waves crush their shells into powder. That powder mixes with white sand, creating beaches that blush like sunset. The pink is actually life itself, ground down and scattered across the shore. Hawaii offers green sand beaches, rare and strange. Papakalea Beach on the Big Island glitters with olivine crystals. Olivine forms deep inside Earth in the super-hot mantle. Volcanic eruptions bring it to the surface. The crystals are heavier than regular sand, so they stay put, while lighter particles wash away. What remains is a beach the color of jade, sparkling green in the tropical sun. White sands in New Mexico isn't even made of regular minerals. It's gypsum, the same stuff in drywall and chalk. This desert holds the largest gypsum dune field on Earth. The white is so bright, it almost hurts to look at. On hot days, the sand stays surprisingly cool because gypsum reflects heat instead of absorbing it. You can walk barefoot across dunes at noon without burning your feet. Glass Beach in California is different again. It's man-made beauty born from trash. For years, people dumped garbage there. Broken bottles, old dishes, shattered glass. The ocean didn't care that it was waste. Waves tumbled the glass for decades, smoothing sharp edges, polishing surfaces, until every piece became a jewel. Now, the beach is covered in smooth pebbles of glass. Blues, greens, browns, clear pieces that catch the light. Nature transformed human carelessness into something beautiful. Australia has white sand beaches so pure they squeak when you walk on them. The sand is almost 100% quartz, worn down to powder over millions of years. Whitehaven Beach is famous for sand so clean you could use it to polish silver. It's soft as flour and stays cool even in blazing heat. Each color is a signature. Black says volcano. Pink says coral reef. Green says ancient mantle. White says pure quartz. Brown says iron. Red says rust. The beach doesn't just tell you where you are. It tells you what happened there, sometimes millions of years ago. So sand isn't just old. It's not just abundant. It's also an artist. Earth takes minerals, shells, lava, crystals, even broken glass, and turns them into beaches. Each one is different. Each one is beautiful. and each one invites you to rest on billions of stories, painted in colors that range from midnight black to blushing pink to emerald green. Sand doesn't just show beauty through color. Sometimes it speaks. There are places on Earth where sand dunes actually sing. Walk across certain deserts and you'll hear it. A low hum, a rumble, sometimes even a booming sound like distant thunder. The sand is making music. This isn't legend or imagination. It's real physics creating something that feels like magic. Scientists call them singing sands or booming dunes. They exist in about 40 places worldwide. The Gobi Desert has them. So does the Sahara. There are singing dunes in California, in Nevada, in the deserts of Oman and Chile. The sound happens when sand grains slide down the face of a dune. But not just any sand will sing. The grains need to be almost perfectly round and almost exactly the same size. They need to be dry, and they need to move together in just the right way. When all these conditions align, the grains vibrate as they tumble. Those vibrations create sound waves. The whole dune becomes a musical instrument. The tone depends on the dune's size. Small dunes produce higher notes. Massive dunes create deep bass rumbles you feel in your chest. Some dunes hum at exactly 90 Hz. Others boom at 60. The sound can last for minutes, echoing across empty desert. Local people have known about singing sands for thousands of years. Marco Polo wrote about hearing spirit voices in the desert. Ancient travelers thought the sounds were supernatural warnings. Some cultures believed demons lived in the dunes. Others thought gods were speaking. They were hearing sand, just sand, making music through nothing but friction and physics. Scientists studied these dunes for years, trying to understand exactly how it works. They discovered that when you disturb the surface, even slightly, you create a chain reaction. One grain bumps the next. That grain bumps another. Soon, billions of grains are moving together in waves. They synchronize, vibrating at the same frequency. That synchronization amplifies the sound. It's like the dune is breathing, like it has a voice. Walk across Kelso Dunes in California, and you might hear a sound like a distant cello. Disturb the sand on Singing Mountain in Nevada, and you'll hear a boom that carries for miles. The sound is so strange, so unexpected in the silence of the desert, that it stops you in your tracks. Not every sand dune can sing. Most stay silent no matter what you do. The singing ones are rare, requiring conditions so specific they're almost accidental. The grains need to be quartz. They need to be polished smooth by wind over thousands of years. They need to be free of dust and moisture. Everything has to be perfect. When it is perfect, the experience is unforgettable. Imagine standing on a dune at sunset. The desert is quiet except for wind. You take a step. The sand beneath your feet begins to hum. The sound grows. It vibrates through your legs, into your bones. The entire dune is resonating. You're standing on an instrument that plays itself, a natural phenomenon that turns geology into symphony. Sand, that humble material we barely notice, becomes a singer. It finds its voice in the emptiness of deserts, humming songs that no human composed, melodies written by nothing but time and wind, and the patient work of making everything smooth. Sand's connection to us goes deeper than music or color. It's literally inside you right now. Silicon, the main element in sand, is in your body. In your bones, your skin, your blood. You're built partly from the same material as beaches and deserts. Most people don't know this. We think of our bodies as organic, separate from rocks and minerals. But silicon is the third most abundant trace element in human tissue. Only iron and zinc are more common. Without silicon, your body wouldn't work properly. Your bones need it. Silicon helps your body use calcium to build strong bone tissue. It activates the enzymes that create collagen, the protein that gives bones flexibility. Without enough silicon, bones become brittle. Children who don't get enough silicon during growth sometimes develop skeletal problems. The element literally helps shape your frame. Your skin contains silicon too. It's concentrated in the outer layer, the part that faces the world. Silicon helps maintain skin elasticity. It supports the connective tissue that keeps skin firm. As people age, silicone levels in skin decrease. That's partly why older skin loses some of its flexibility. The sand element is fading. Hair and nails grow stronger with silicon. The element helps create keratin, the tough protein that forms these structures. Studies show that silicon supplements can make hair thicker and nails harder. The connection between sand and beauty is real and measurable. Even your blood vessels contain silicon. It's found in the walls of arteries, helping maintain their structure and flexibility. Silicon concentrations are highest in the aorta, your body's largest artery. Scientists think it helps prevent arterial hardening, keeping blood flowing smoothly. Where does this silicon come from? Your diet. Whole grains contain silicon. So do green beans, bananas, spinach, and beer. Your body extracts the silicon, converts it into a usable form, and incorporates it into growing tissue. You're slowly building yourself from transformed sand. The silicon in your body isn't exactly the same as beach sand anymore. Your digestive system converts solid silicon dioxide into soluble forms that cells can use. But the source is the same. The silicon atoms in your bones were once part of rocks, mountains, sand grains. They were freed by weathering, dissolved by water, absorbed by plants, and eventually consumed by you. This means something poetic. You're not separate from Earth. You're made from it. The ground beneath your feet and the structure inside your body share the same building blocks. When you walk on sand, you're walking on distant relatives of your own bones. Ancient peoples somehow understood this connection. Many cultures used ground minerals in medicine. They made clay poultices for wounds. They consumed specific earths for healing. Modern science dismissed this as superstition for years. But research now shows some of these practices had merit. The minerals in Earth, including silicon, do affect human health. Your body replaces its silicon constantly. You absorb some from food. You lose some through urine. The silicon in your bones today won't all be there next year. You're in constant exchange with the Earth, trading atoms back and forth in a cycle that connects you to soil and sand. So when you touch sand, remember this. you're touching something that's also touching you from the inside. The boundary between you and the world is thinner than you think. You're walking, breathing, living proof that humans and Earth are built from the same ancient materials. Sand isn't just connected to life. Sometimes life actually creates it. Right now, in warm, tropical waters, fish are making beaches. They're called parrotfish, and they're some of the hardest working builders on Earth. Parrotfish have beaks, not exactly like bird beaks, but close. Their teeth are fused together into hard plates that look and work like parrot beaks. They use these beaks to scrape algae off coral reefs. But here's the thing. When they scrape the algae, they also scrape the coral itself. They bite chunks right off the reef, coral and all. Then they eat it. The whole thing goes down. They digest the algae for nutrients. But the coral, which is mostly calcium carbonate, passes straight through their system. It comes out the other end as powder. Fine, white powder. That powder is sand. One large parrotfish produces about 200 pounds of sand per year. Think about that. A single fish, just going about its day, eating and pooping, creates more sand than you could carry. A busy reef with hundreds of parrotfish is a sand factory running 24 hours a day. This is where much of the Caribbean's famous white sand comes from. Those pristine beaches in the Bahamas, in Jamaica, in Turks and Caicos. Fish poop, beautiful, powdery, perfect white sand that millions of tourists walk on every year. All of it passed through the digestive system of parrotfish. The process is surprisingly fast. A parrotfish can take thousands of bites per day. Each bite scrapes a little coral. Over weeks and months, those bites add up. Scientists have measured it. A healthy reef with a good parrotfish population can produce tons of sand annually. The fish are literally building the beaches bit by bit, meal by meal. Different species make different amounts. The blue parrotfish is one of the biggest producers. They can reach 4 feet long and spend most of their day chomping coral. Smaller species contribute less, but there are more of them. Together, parrotfish populations can reshape coastlines over decades. This also means parrotfish are critical to reef health. They keep algae under control, preventing it from smothering coral. They create sand that builds beaches and lagoons. They're gardeners and construction workers rolled into one colourful package. Lose the parrotfish, and you lose the beaches they build. Some islands have learned this the hard way. Overfishing parrotfish leads to algae overgrowth on reefs. It also means less new sand. Beaches stop growing. Some even shrink as waves carry existing sand away without new sand replacing it. The fish are more important than anyone realized. Watch a parrotfish feed, and you're watching geology in action. Each bite is a tiny construction project. The fish doesn't know it's making beaches. It's just hungry, just doing what parrotfish have done for millions of years. But the result is real and measurable. Islands exist partly because these fish exist. So, next time you sink your toes into white Caribbean sand, remember where it came from. Remember the fish that made it, the coral it used to be, the reef ecosystem that supports the whole process. That beautiful beach is alive in a way. It's constantly being created by creatures that turn eating into building, that transform rock into powder, that make walking on the shore possible for you and for millions of others. Sand builds beaches over time, but sand also measures time itself. For thousands of years, humans have used sand to mark the passing of moments. The hourglass is one of our oldest timekeeping tools, and it works because sand has a special relationship with gravity and flow. Pour sand through a narrow opening and something remarkable happens. The grains fall at an almost perfectly steady rate. Not too fast, not too slow. Each grain follows the one before it in a rhythm so consistent you can measure minutes by it. This is why hourglasses work. Sand is predictable. But why sand? Why not water or dirt or anything else? Sand grains are just the right size. Too small and they clump together with static electricity. Too large and they jam in the narrow neck. Sand grains, when properly sized, flow like a liquid but act like a solid. They slide past each other smoothly, one after another, creating that hypnotic stream. The first hourglasses appeared around the 8th century, though nobody knows exactly who invented them. Sailors loved them because, unlike water clocks, hourglasses worked on rocking ships. The motion didn't affect the sand's flow. Sea captains used them to time watches, to measure sailing speed, to mark the hours during long voyages across dark oceans. Medieval monks used them to time prayers. Preachers used them to measure sermons. Cooks used them to track baking times. The hourglass became a symbol of time itself, appearing in art and literature as a reminder that our moments are always falling away, grain by grain, never stopping. Watch an hourglass closely. Really watch it. The sand doesn't fall in a steady stream immediately. First, a cone forms inside the top chamber. The sand funnels toward the center, creating a hollow space. Then grains begin dropping through the neck, one by one at first, then in a steady flow. The pile in the bottom chamber grows slowly, forming its own perfect cone. The shape of that growing pile follows mathematical rules. The angle of repose, scientists call it. Sand naturally forms slopes at about 34 degrees. Steeper, and the pile collapses. Shallower, and it's not using the available space. Sand knows this angle without thinking. It finds it every time. There's something meditative about watching sand fall. Your mind quiets. Your breathing slows. The steady stream creates a focus point, something to watch without thinking. This is why people put hourglasses on their desks, not just for timing things, but for the calm they bring. The visible reminder that time moves whether we worry or not. Modern hourglasses are precisely calibrated. The sand is carefully sized and dried. The glass is shaped exactly right. The opening is measured to the millimeter. A well-made hourglass can measure time as accurately as many digital clocks. The sand completes its fall in exactly 1 hour, or 3 minutes, or 30 seconds, depending on its design. But hourglasses teach us something beyond measurement. They show us that time isn't just a number on a screen. It's physical. It has weight and movement. Each second that passes is real enough to see, real enough to hold in your hand as a grain of sand. Time isn't abstract. It's as concrete as the sand that measures it. And when the sand runs out, you can flip it over. Start again. Give yourself another hour, another chance, another cycle of grains falling through darkness into light. Time changes sand slowly through weather and waves. But sometimes change happens in an instant. Sometimes the sky falls and sand transforms in seconds. The result is desert glass, and it's some of the most mysterious material on Earth. The Sahara Desert holds vast fields of yellow-green glass scattered across the sand. It's called Libyan desert glass, and pieces of it litter the ground for hundreds of square miles. Pick one up, and it's surprisingly light, full of bubbles and swirls, translucent like frozen honey. Beautiful, strange, and nobody was sure how it got there. Scientists debated for decades. The glass is almost pure silica, around 98%. That's purer than most natural glass. It's also very old, dating back about 29 million years. Something happened in the Sahara long ago, something hot enough to melt sand into glass across huge areas. The answer came from studying impact craters. When a meteorite slams into Earth, the energy is immense. The impact generates temperatures over 3,000 degrees Fahrenheit, hot enough to vaporize rock, hot enough to turn sand into liquid in milliseconds. That liquid cools quickly, becoming glass before it can form back into crystals. The Libyan glass formed this way. A meteorite, probably huge, struck the Sahara millions of years ago. The impact melted the desert sand instantly. The molten material splashed outward, cooling as it flew through the air. Some pieces landed miles from the impact point. The glass scattered across the desert, where it's been sitting ever since. The same process created other desert glasses around the world. There's fulgurite, glass formed when lightning strikes sand. A lightning bolt carries more electrical energy than anything natural except the sun. When it hits the ground, it instantly melts sand into twisted tubes of glass, following the path the lightning took underground. These lightning sculptures can be several feet long, hollow, with rough outer surfaces and smooth glassy interiors. Then there's trinitite, the glass formed at the Trinity nuclear test site in New Mexico. The first atomic bomb test in 1945 melted the desert sand into a thin layer of radioactive green glass. It's still there, forbidden to collect, but impossible to completely remove. Human fire, hot as the sun, turning sand to glass just like meteorites do. All these glasses share something. They're born from violence, but end up beautiful. The destructive force that creates them is terrible. Explosions, cosmic impacts, lightning strikes. But what they leave behind catches light, holds color, becomes something people want to keep and study and admire. Ancient Egyptians found Libyan desert glass and carved it into jewelry. King Tutankhamun's tomb contained a scarab carved from the yellow-green glass. They didn't know it came from space. They just knew it was special, was different from any gem they'd seen before. Today, scientists study desert glass to understand impacts, to learn about extreme temperatures and pressures, to see what happens when worlds collide. Each piece is a frozen moment of catastrophe. The glass remembers heat beyond imagining, force that could level mountains, energy that turned solid ground to liquid in a blink. But hold a piece of desert glass now, and it's cool in your hand. Smooth, peaceful. The violence is long over. What remains is only beauty, only wonder, only evidence that even destruction can create something worth keeping. Sand transformed by cosmic fire into windows that let light through. Desert glass stays where it falls. But most sand doesn't stay anywhere for long. Right now, while you rest, sand is traveling through the air above you. Tiny particles from deserts thousands of miles away are floating in your home. They're in your lungs, on your furniture. Sand goes everywhere. Scientists call it mineral dust. It's sand ground so fine that air can lift it. Wind picks up these microscopic particles from deserts and carries them across continents, over oceans, around the entire world. Every year, billions of tons of dust circle the planet. The Sahara is Earth's biggest dust exporter. Storms lift sand high into the atmosphere, sometimes reaching altitudes of 15,000 feet. Trade winds catch these dust clouds and push them west across the Atlantic Ocean. 5 days later, Saharan dust reaches the Caribbean. A week after that, it's raining down on the Amazon rainforest. This dust isn't trash, it's fertilizer. Saharan sand contains phosphorus and other nutrients that rainforests need. The Amazon actually depends on African dust to stay healthy. About 22,000 tons of Saharan dust settle in the Amazon basin every year, replacing nutrients that rain washes away. The world's largest desert feeds the world's largest rainforest. The same dust reaches North America. People in Florida sometimes see red sunsets caused by Saharan dust filtering the light. Cars get coated with fine orange powder. The dust has traveled 3,000 miles, crossing an ocean, still recognizable as African sand. Asian deserts send their dust east toward North America's west coast. Spring dust storms in the Gobi Desert lift sand that lands in California a week later. Scientists can trace the chemical signature back to specific regions in China and Mongolia. The dust remembers where it started. Even your house dust contains sand from far away. Scientists have analyzed dust collected from homes and found particles from deserts hundreds or thousands of miles distant. The air conditioning pulls it inside. It settles on shelves and floors. You breathe it without knowing. Your home is accumulating geology from around the world. This traveling dust does more than feed forests. It affects climate. Dust particles reflect sunlight back into space, cooling the planet slightly. They also seed clouds. Water vapor needs something to condense on, and dust particles work perfectly. Many clouds form around traveling sand grains. Weather patterns shift based on where dust travels. Dust storms can be enormous. Haboobs, the Arabic word for intense dust storms, create walls of sand thousands of feet high. They roll across deserts like solid waves, turning day into night in seconds. Phoenix, Arizona experiences haboobs that look apocalyptic, towering clouds of dust swallowing the city. But even gentle days have invisible dust everywhere. Studies show that dust levels have increased globally as deserts expand. More sand is traveling farther than ever before. Your connection to distant deserts is getting stronger whether you know it or not. Ancient people understood this better than we do now. They saw dust storms as omens, as evidence that Earth is one connected system. They were right. The Sahara and the Amazon breathe together. Asia and America share the same air, the same dust, the same tiny particles of wandering sand. You're part of this exchange too. Some of the dust in your home will eventually leave, caught by wind, carried back outside, lifted high, and sent somewhere new. Sand that rested briefly in your life will move on to touch someone else's world. Sand travels through air, but it also does something quieter and more important. It cleans water. Right now, beneath beaches and riverbeds, sand is purifying billions of gallons of water without any human help. It's been doing this job for millions of years. When rain hits the ground, it starts moving downward through soil and sand. Each grain acts as a tiny filter. Water squeezes through the spaces between grains, and as it does, impurities get stuck. Bacteria catch on grain surfaces. Particles too large to fit through narrow gaps stay behind. The water keeps moving, getting cleaner with every layer it passes through. Beach sand is especially good at this. The constant washing by waves has sorted the grains by size, creating layers that filter in stages. Large particles get caught in the upper layers. Smaller contaminants are trapped deeper down. By the time water reaches the water table below the beach, it's surprisingly pure. This natural filtration creates aquifers. These are underground layers of rock and sand that hold clean water. The sand acts like a living filter, constantly purifying water as it flows through. Many cities get their drinking water from aquifers. They're tapping into water that sand cleaned without chemicals, without machinery, without anything but patience and time. The process is slow. Water might take years to seep through enough sand to become completely pure, but the result is worth the wait. Naturally, filtered water tastes different than chemically treated water. It's softer, cleaner, with minerals absorbed from the rock and sand it passed through. Ancient people understood this instinctively. They dug wells near rivers and beaches, knowing the water there would be clean. They didn't know about bacteria or contamination, but they knew sand-filtered water was safer to drink. That knowledge kept civilizations alive. Modern water treatment plants copy what sand does naturally. Many use sand filters as a key step in purification. Water flows through beds of carefully graded sand, just like in nature, but faster and more controlled. The sand still does the real work, catching particles and bacteria the same way it has for eons. The size of the gaps between sand grains matters enormously. Too large and contaminated water flows through without cleaning. Too small and water barely moves at all. Beach sand usually has the perfect spacing by accident. Waves sort grains into just the right sizes over thousands of years. Sand filters also work in reverse. When high tide pushes salt water up onto a beach, the sand filters out the salt as the water seeps down. The water that reaches the aquifer below is fresh, not salty. The sand somehow knows how to separate salt from water using nothing but tiny spaces and gravity. This filtering happens constantly. Every raindrop that falls eventually meets sand. Every stream feeds into larger rivers that flow over sandbars. Every beach is cleaning ocean water and catching pollutants before they spread. Sand is one of Earth's maintenance crew, quietly keeping water systems functional. Without this natural filtration, life on land would be much harder. We'd have less access to clean water. Rivers would carry more contamination. Aquifers would be polluted beyond use. But sand keeps working, keeps cleaning, keeps making water safe to drink. It does this everywhere, all the time, asking nothing in return. Sand filters water safely. But mix sand and water the wrong way, and you get something people have feared for generations. Quicksand. Movies show it as a death trap that swallows people whole. Heroes sink slowly, struggling, disappearing into the earth. It looks terrifying. It's also mostly wrong. Real quicksand exists, but it's not the monster movies made it. It forms when water saturates sand completely, filling every gap between grains. The water pressure pushes the grains apart slightly. The sand stops acting like solid ground. It becomes something between liquid and solid, a substance that can't support weight normally. Step on real quicksand and you sink. But here's the surprising part. You can't sink completely. It's physically impossible. Quicksand is denser than the human body. You're more likely to float than drown. Your body will sink until you're roughly waist deep. Then buoyancy stops you from going further. The danger isn't the sinking. It's the panic. When people feel themselves sinking, they thrash and struggle. That makes things worse. Rapid movement creates suction between your body and the sand. The suction makes it much harder to pull yourself free. People have died in quicksand, but usually from exhaustion, dehydration, or drowning when tides came in, not from being swallowed. The physics is actually fascinating. Quicksand behaves like a non-Newtonian fluid. Push on it slowly and it stays liquid, letting you move. Push hard and fast and it solidifies, gripping whatever disturbed it. Your panicked thrashing makes the sand grab you tighter. Staying calm keeps it liquid and easier to escape. Scientists have studied the best escape method. First, don't panic. Easier said than done, but essential. Second, lean back slowly. Increase your surface area like you're trying to float. This distributes your weight and prevents further sinking. Third, make slow swimming motions to work your legs free. It takes time, sometimes hours, but it works. Quicksand forms in specific places. River deltas where fresh water meets salt water. Underground springs that push water up through sand. Beaches where tides create waterlogged patches. Earthquake zones where shaking liquefies the ground temporarily. These aren't random traps. They're predictable if you know what to look for. Certain animals handle quicksand better than humans. They instinctively avoid struggling. A deer caught in quicksand will often stay still, waiting for the sand to solidify slightly before carefully extracting itself. Animals seem to know that patience works better than strength. The fear of quicksand peaked in the 1960s and 70s. It appeared in dozens of movies and TV shows, always as a deadly hazard. An entire generation grew up thinking quicksand was a major life threat. In reality, quicksand deaths are extremely rare. You're far more likely to be struck by lightning. But the fear wasn't completely invented. Quicksand used to be more dangerous when people wore heavy clothing and equipment. A person in thick clothes carrying a heavy pack could sink deeper and struggle more. Modern lightweight clothing makes escape easier. The truth about quicksand is less dramatic, but more interesting than the myth. It's a temporary state that sand enters when conditions align. It's strange and unsettling, but not particularly deadly. It's a reminder that sand, even when mixed with water, still follows physical laws. Understanding those laws turns terror into something manageable, something you can work with instead of against. Quicksand looks dangerous until you understand it. Sand itself transforms completely when you really look at it. Take a single grain and put it under a microscope. What you see stops looking like sand at all. It becomes an alien landscape, a tiny world you never knew existed. A magnified sand grain reveals incredible detail. Sharp crystal faces catch the light at angles. Colors appear that your naked eye missed. Reds, blues, greens, purples, all shimmering inside what looked like plain tan sand. Each grain is a gemstone too small to appreciate without help. But the shape tells the real story. Look at sand from a young mountain river and you see jagged grains with sharp edges. These are babies in geological terms, barely worn down. They haven't traveled far. Now, look at beach sand under the same magnification. The grains are smooth, polished, rounded by thousands of years of tumbling. You're seeing time written in smoothness. Some grains contain entire worlds inside them. Fossils of microscopic creatures are embedded in the crystal structure. Tiny shells, ancient plankton, remnants of life from millions of years ago. A single grain might hold dozens of these fossils, an entire ecosystem frozen in stone. Other grains are pure mineral crystals. Quartz is common, clear or cloudy, sometimes with inclusions of other minerals trapped inside. Feldspar grains show geometric crystal patterns. Mica grains are flat and shiny, splitting into layers like tiny books. Each mineral has its own personality, its own way of catching light. Volcanic sand reveals its violent origin under magnification. The grains are actually glass shards with sharp, irregular edges. Frozen bubbles appear inside the glass, air trapped when lava cooled instantly. Some grains are hollow shells, all that remains of larger bubbles that popped. The most surprising discoveries are biological. Radiolarian shells appear in some sand. These are single-celled organisms that build intricate geometric shells from silica. Their shells are architectural marvels, complex spheres and stars, and cages that seem impossibly delicate. After the radiolarian dies, its shell becomes part of the sand. Diatoms leave similar structures. These microscopic algae create glass shells in thousands of different patterns. Circles with holes like wheels, pillboxes with intricate lids, cylinders covered in fine pores. Under high magnification, they look like alien spacecraft or impossible clockwork. They're common in beach sand, billions of them, each one a tiny masterpiece. Scientists use these microscopic features to identify where sand came from. Like fingerprints, each beach has a unique mix of grain types, shapes, and inclusions. Sand from Maine looks different from sand in California, even under a basic microscope. Sand from Hawaii is completely distinct from sand in Florida. This microscopic diversity means that every handful of sand contains thousands of different stories. Not just one journey from mountain to shore, but thousands of journeys. Each grain took its own path. Some came from nearby, others traveled across continents. Some are young, others are ancient beyond measuring. All of them ended up together in your hand. The microscope reveals that sand isn't a single thing. It's a collection of individuals, each unique, each carrying its own history, written in shape and color and internal structure. What looks uniform from a distance becomes impossibly diverse up close. Sand teaches us that complexity hides in simplicity, that closer inspection always reveals more than we expected. Every grain looks different under a microscope, but sand also sounds different depending on where you walk. Your footsteps on sand create music you rarely notice. Each type of sand has its own voice. Walk across dry beach sand and you hear a soft crunch. The grains compress and slide past each other, creating friction. The sound is gentle, almost whispering. It's the noise of countless tiny collisions happening with each step. The drier the sand, the louder the sound. Moisture acts as a lubricant, quieting the friction between grains. Wet sand near the waterline sounds completely different. It's denser, more solid. Your footsteps produce a muted thud instead of a crunch. The water fills the gaps between grains, creating a surface that acts more like mud than dry sand. There's less air, less space for sound to resonate. Some beaches squeak when you walk on them. This happens on beaches with very round, very uniform quartz grains. When pressure forces these grains past each other, they vibrate at specific frequencies. The vibration creates a sound between a squeak and a whistle. Whitehaven Beach in Australia is famous for squeaking sand. The sound is loud enough to startle first-time visitors. Desert sand sounds different entirely. Walk across a desert floor and you hear almost nothing. The sand is so fine and loose that your foot sinks without much resistance. The grains flow around your steps like water, silent and smooth. Only when wind blows does desert sand make noise, hissing as billions of grains skip across the surface. Volcanic black sand has its own acoustic signature. The grains are often coarser and more angular than beach sand. Walking on it produces a grinding sound, rougher and sharper than the soft crunch of quartz sand. The irregular shapes create more friction, more resistance, more noise with each step. Indoor sand, the kind used in sandboxes or hourglasses, sounds different because it's processed. The grains are cleaned and sorted by size. They're often tumbled to remove sharp edges. The result is sand that sounds uniform, consistent, almost artificial. It lacks the random variation that makes natural sand interesting. Scientists have actually studied these sounds. They call it acoustic ecology, the study of sound in different environments. Sand acoustics reveal information about grain size, moisture content, and mineral composition. You can identify a beach by the sound of footsteps if you know what to listen for. Children instinctively understand sand sounds. Watch a kid on a beach, and they'll often stomp deliberately to hear the crunch. They'll drag their feet to make longer sounds. They're experimenting with the acoustic properties of sand without knowing the science behind it. The The sound also changes with speed. Walk slowly and you hear individual grains shifting. Run, and the sounds blend into a continuous rushing noise. Jump, and you create a sudden loud impact, followed by a cascade of quieter settling sounds as disturbed grains find new positions. Even the same beach sounds different at different times. Morning sand, cool from the night, sounds crisper. Afternoon sand, heated by sun, sounds softer. The temperature changes how grains interact, how they compress, how they vibrate when disturbed. These sounds are information. Your brain processes them without thinking, using the acoustic feedback to judge surface stability. You walk differently on squeaky sand than on silent desert sand, because the sound tells you about traction and firmness. Sand tells you things through sound and touch. Ancient people listened and learned. They discovered that sand could heal as well as build. For thousands of years, humans have used sand in ways that seem strange now, but made perfect sense then. Japan still practices sand bathing. People bury themselves in naturally heated volcanic sand on certain beaches. Only their heads stick out. The hot sand surrounds their bodies, warming them deeply. The heat relieves joint pain and improves circulation. The weight of the sand creates gentle pressure that many find calming. Modern studies show these sand baths actually work, reducing inflammation and easing muscle tension. Egyptian physicians prescribed sand treatments 3,000 years ago. They understood that hot sand could draw out infections. Wounds were sometimes packed with clean desert sand to stop bleeding and promote healing. The silica in sand has mild antiseptic properties. It wasn't magic. It was practical medicine based on careful observation. But sand's biggest contribution to humanity is construction. Every ancient civilization built with sand. Egyptian pyramids used limestone blocks held together with sand-based mortar. The Colosseum in Rome stands on concrete made from volcanic sand mixed with lime. Sand is the foundation of human architecture, literally and figuratively. Sandstone temples dot India, carved directly from compressed ancient beaches. These structures have survived centuries because builders understood how sand behaves. They knew which sandstone layers were strong enough to carve. They knew how to orient blocks so natural bedding planes added strength rather than weakness. Medieval European cathedrals used sand in their mortar and as the base material for colored glass. Crushed sandstone mixed with lime created mortar that's still solid after 800 years. Some medieval mortar is harder than the stones it holds together. The secret was in choosing the right sand and mixing it properly. Islamic architecture made sand an art form. Builders in desert regions developed techniques for stabilizing sand dunes and building on unstable ground. They created structures that have lasted centuries in harsh conditions. Their knowledge of sand properties was sophisticated, passed down through generations of master builders. Native Americans used sand in ceremonies and as a building material. Pueblo peoples mixed sand with clay to make adobe bricks. The sand prevented the clay from cracking as it dried. It also made the bricks more resistant to water damage. These buildings still stand in the American Southwest, proof that the mixture works. Sand casting allowed humans to make metal tools and weapons. Pour molten metal into a sand mold, and it takes the exact shape you carved. The sand withstands intense heat without melting. When the metal cools, break away the sand, and you have a perfect casting. This technique enabled the Bronze Age, the Iron Age, all of metallurgy. Today, we still depend on sand for construction. Concrete is mostly sand. So is asphalt. Glass is melted sand. Computer chips start as purified silicon extracted from sand. Your smartphone, your windows, your roads, your buildings, all of them began as sand somewhere. We've been building with sand for so long that we forget it's remarkable. This common material is strong enough to support skyscrapers, pure enough to make glass, versatile enough to heal and create. Ancient peoples treated sand with respect because they understood its value. We use more sand than they could imagine, but think about it less. Humans have used sand for thousands of years, but every grain we've ever touched was on a journey long before we arrived. Let's follow one grain from beginning to end, from the moment it breaks free until it reaches the sea. Our grain starts as part of a granite peak high in the mountains. It's locked inside solid rock, surrounded by other minerals, part of something massive and permanent. Then one winter, water seeps into a crack near our grain. The water freezes. Ice expands with tremendous force. The crack widens. After dozens of freeze-thaw cycles, a chunk of granite breaks free and tumbles down the mountainside. The chunk shatters when it hits the valley floor. Our grain is still attached to other minerals, still part of something larger. But now it's moving. Snowmelt creates a stream that pushes the rock fragment downstream. It rolls and bounces, hitting other rocks, breaking smaller with each impact. Years pass, maybe decades. The rock fragment wears down. Other minerals, softer than quartz, erode away first. Eventually, our grain separates completely. It's now individual, a single grain of quartz sand, roughly 0.5 millimeter across. The journey is just beginning. The stream carries our grain through foothills, into a larger river. The current pushes it downstream during spring floods, then deposits it on a gravel bar during low water. It sits for months, sometimes years, before the next flood moves it again. Progress is slow. The river carries the grain maybe a few miles each decade. Other grains join ours. Some are fresh from the mountains. Others have been traveling for centuries. They tumble together, grinding against each other, getting rounder and smoother. Our grain loses its sharp edges. It becomes polished, shaped by friction into something approaching a perfect sphere. The river reaches flat plains. The current slows. Our grain settles in a muddy bank and stays there for 1,000 years. Grass grows over it. Trees take root. Civilizations might rise and fall, while our grain sits buried under vegetation. Then a flood changes the river's course. The bank erodes. Our grain is moving again. Now the river is huge, carrying massive volumes of water toward the ocean. Our grain travels faster, suspended in the current rather than rolling along the bottom. It passes cities, bridges, boats. People stand on the shore having conversations while our grain flows past, invisible in the muddy water, continuing its ancient journey. The river mouth approaches. Fresh water meets salt water. The current slows dramatically. Our grain settles to the bottom in the delta, joining billions of other grains in the same situation. This could be the end. Many grains stay trapped in deltas for millions of years, eventually becoming sandstone. But our grain gets lucky. A storm tide pushes into the delta. The strong current picks up our grain and carries it into the ocean. Waves take over. They push our grain up onto the beach, then pull it back. This happens thousands of times. Gradually, the waves move our grain along the shore, mixing it with other grains, burying and exposing it repeatedly. Finally, our grain reaches a stable spot halfway up a beach. It settles between other grains, packed tightly. The sun warms it during the day. It cools at night. Occasionally, someone steps on it without knowing. It has traveled from mountain peak to sea level, covering hundreds of miles over hundreds of thousands of years. Our grain rests on a beach, but it might not stay there. Wind picks up dry sand and carries it inland, building dunes. These dunes look solid and permanent. They're not. They flow like liquid, just incredibly slowly. Desert dunes are rivers of sand moving in slow motion. Stand on a dune, and you're standing on something migrating across the landscape. Most dunes move between 10 and 30 feet per year. You can't see it happening, but satellite photos taken years apart show dunes in completely different positions. They creep forward like frozen waves, always advancing, never stopping. The movement follows a pattern. Wind hits the gentle slope on one side of the dune, the windward side. It picks up grains and carries them up this slope. When the wind reaches the top, it loses strength. The grains drop on the other side, the steep side called the slip face. This side stays steep at about 34 degrees, the natural angle that sand forms. As grains keep piling on the slip face, the whole dune shifts forward. The front gets taller. Eventually, it becomes unstable. A small avalanche occurs, sending grains tumbling down. This happens constantly in tiny increments. Each avalanche moves the dune forward by fractions of an inch. Add up millions of these small avalanches, and the dune migrates miles. Some dunes move faster than others. Smaller dunes migrate quicker than large ones. A small dune with less mass is easier for wind to reshape. Massive dunes called megadunes can be 600 feet tall and barely move a few feet per year. But they're still moving, still flowing forward. Dunes also create patterns. Seen from above, deserts show waves and ripples frozen in sand. Crescent dunes look like smiles or horns pointing downwind. Star dunes have arms radiating from the center like starfish. Linear dunes form parallel lines stretching for miles. Each shape tells you about the wind patterns that created it. The Great Dunes in Colorado form a dune field against a mountain range. Winds carry sand toward the mountains. The sand piles up against this barrier, unable to cross. The result is massive dunes that recycle the same sand endlessly. Wind pushes grains up the dune. They cascade down the other side. Then wind picks them up again. The sand is trapped in a loop, flowing but never escaping. China's singing sand dunes move despite heavy tourism. Thousands of people climb them daily. The human traffic should disrupt the natural flow, but the dunes keep their shape and keep migrating. The volume of sand is so vast that human interference is barely noticeable. The dune absorbs the disruption and continues its slow march. Desert cities sometimes find themselves in the path of advancing dunes. In Mauritania, the city of Chinguetti fights a constant battle against encroaching sand. Dunes threaten to bury buildings. Residents dig out their homes repeatedly. The dunes don't care. They keep flowing forward, following wind patterns that existed long before the city. This flowing quality makes dunes feel alive. They respond to wind the way water responds to current. They form channels and pools. They split and merge. They create eddies and backflows. Watch a desert during a windstorm, and you can see the surface moving, grains skipping and jumping, the dune adjusting its shape in real time. The Sahara's dunes are migrating south, pushed by changing wind patterns. They're swallowing farmland and villages, advancing at measurable rates. The desert is expanding, flowing like a slow tide across North Africa. Dunes respond to wind, but sand also responds to heat in ways that shape your experience at the beach. Walk barefoot on sand at noon, and you'll dance across it, burning your feet. Return at sunset, and the same sand feels cool and pleasant. Sand has a strange relationship with temperature. Sand heats up fast because it doesn't hold water well. Wet materials take longer to heat because water absorbs energy efficiently. Dry sand has air gaps between grains instead of water. Air is a terrible conductor of heat. So when the sun hits sand, the energy goes directly into heating the grains themselves, rather than being absorbed by moisture. The top layer gets scorching hot. Touch it, and you pull your hand back immediately. But dig down just a few inches, and the sand feels surprisingly cool. The air gaps between grains prevent heat from traveling downward efficiently. Each grain heats up individually, but struggles to transfer that heat to neighboring grains. The result is extreme temperature on the surface, but coolness just below. This is why animals bury themselves in sand during hot days. Lizards do it, crabs do it, even some beetles dig down to escape surface temperatures that would kill them. A few inches of sand provide effective insulation from the blazing heat above. At night, the process reverses just as quickly. Sand radiates heat back into the air faster than almost any natural surface. Within an hour after sunset, hot beach sand becomes cool. Within 2 hours, it might feel cold. The lack of water means nothing holds the heat in. It escapes as quickly as it arrived. This rapid cooling makes deserts famously cold at night. The same sand that burned your feet at 2 in the afternoon might be near freezing by 2 in the morning. Temperature swings of 60 degrees or more are common. The sand stores almost no thermal energy between day and night. Different colored sands heat at different rates. Black volcanic sand gets hotter than white quartz sand under the same sunlight. The black absorbs more light energy while white reflects it. Stand on black sand beaches in Iceland or Hawaii at midday, and the heat is almost unbearable. The white sands of New Mexico stay much cooler. Scientists use this property to study climate. Sand dunes preserve temperature information in how grains are arranged. Certain patterns only form in specific temperature ranges. Ancient dune formations tell researchers what the climate was like thousands of years ago based on grain arrangement and bonding patterns. Sand's thermal properties also affect weather. Hot desert sand heats the air above it, creating rising currents that generate dust devils and dust storms. The rapid heating creates instability in the atmosphere. Cooler air rushes in to replace rising hot air, creating wind that picks up more sand, which heats more air, creating a cycle that can build into major weather systems. Buildings in desert regions have used sand's thermal properties for centuries. Thick walls filled with sand stay cool during the day because the sand inside never heats fully through. At night, any heat stored in the sand radiates slowly back, keeping the interior warm. It's natural climate control using nothing but sand's poor heat conductivity. Touch sand at different times and you're feeling the same material behaving completely differently. Morning sand is cool and damp. Noon sand is blazing. Evening sand is perfect. Night sand is cold. One material, constantly changing, cycling through temperatures, responding to the sun's daily journey across the sky. Sand changes with temperature throughout the day, but on certain beaches, something stranger happens at night. The sand glows. Step on it, and blue light spreads from your footprint. Waves breaking on shore create lines of bright blue fire. It looks like magic. It's actually tiny life living in the sand. The glow comes from organisms called dinoflagellates. They're single-celled plankton that produce light when disturbed. Billions of them live in the water along certain coastlines. During the day, they're invisible. At night, any movement triggers them to flash bright blue for a fraction of a second. The effect is stunning. Walk along the beach, and each footstep creates a glowing outline. Kick the water, and you send up a spray of blue sparks. Waves crash, and the entire surf line lights up like electric blue fire rolling onto shore. The glow lasts only moments before fading back to darkness. Scientists call this bioluminescence. The dinoflagellates create light through a chemical reaction inside their cells. When something bumps them, even gently, they release the light as a defense mechanism. The flash might startle predators or attract larger animals that eat the predators. It's a survival strategy that creates one of nature's most beautiful displays. These glowing beaches appear in specific locations. The Maldives has famous bioluminescent shores. So does Puerto Rico, particularly at Mosquito Bay. Parts of California, Australia, and Thailand host seasonal blooms. The dinoflagellates need certain conditions: warm water, specific nutrients, calm bays where they can concentrate without being dispersed. The glow isn't constant. Some nights it's brilliant, other nights it's barely visible. Red tide events, when dinoflagellate populations explode, often produce the brightest displays. During the day, red tide makes water look rust-colored. At night, that same water glows intensely with every wave. The sand itself doesn't glow. The dinoflagellates live in the water and wet sand along the shoreline, but their presence connects them to sand in beautiful ways. As waves wash up the beach, the organisms flow between sand grains. Each grain becomes surrounded by potential light. Disturb the wet sand, and you disturb the dinoflagellates clinging to it. They flash. The sand seems to glow. Other organisms create similar effects. Certain bacteria produce steady green or blue glows rather than flashes. Some jellyfish wash up on beaches and continue glowing for hours. Their light illuminates the sand around them. Small crustaceans, called ostracods, produce blue clouds of light when disturbed in shallow water. People have used bioluminescent organisms for practical purposes. Japanese fishermen tracked certain fish by watching for bioluminescent flashes in their wake. Sailors navigated by the glow of disturbed water, showing where shallow reefs lay hidden. The light was information, readable if you knew how to interpret it. Now, these beaches attract tourists and photographers. Long exposure cameras capture the light as ethereal blue trails in the sand. The photos look surreal, impossible, like special effects. But they're real. Just chemistry and biology creating light without heat, without electricity, using only the energy inside microscopic cells. Standing on a glowing beach connects you to something ancient. Bioluminescence existed before humans, before mammals, before most life forms we recognize today. These organisms have been lighting up oceans for hundreds of millions of years. The sand provides their stage, a dark surface that makes their blue light seem even brighter, even more magical. Bioluminescent organisms need sand to create their displays. But here's something most people don't know. We're running out of sand. Not all sand, not desert sand, but the specific type of sand we need for building. It's disappearing faster than nature can replace it. This seems impossible. Deserts cover huge portions of Earth. Beaches line every coast. How can we possibly run low on sand? The problem is that not all sand works for construction. Desert sand grains are too round, too smooth. Wind polishes them into spheres that don't lock together well. Poor concrete made with desert sand and it's weak, prone to crumbling. Construction needs angular sand with rough edges. River sand and beach sand work perfectly. The grains have enough irregularity to grip each other when mixed with cement. They create strong concrete that lasts decades. This is the sand we're depleting. Humans use about 50 billion tons of sand annually. That makes it the second most consumed resource on Earth after water. We use more sand than oil, more than coal, more than any other solid material. Every building, every road, every bridge requires massive amounts of sand. A single house uses about 200 tons. A hospital needs 3,000 tons. 1 mile of highway requires 80,000 tons. The demand is overwhelming natural supply. Rivers create sand slowly through erosion. It takes thousands of years to produce significant amounts. We're extracting sand from rivers and beaches much faster than new sand forms. The gap is growing. Some countries have already run out. Singapore imported sand from neighboring countries for years to expand its land area. Indonesia, Malaysia, and Cambodia banned sand exports because their own beaches were disappearing. Now, Singapore struggles to find sand sources. Dubai, surrounded by desert, imports sand from Australia because desert sand won't work for their massive construction projects. Sand mining damages ecosystems severely. Dredging sand from rivers changes their flow patterns, causes erosion, and destroys habitats. Beach mining eliminates nesting sites for sea turtles and crabs. Removing sand from one location causes problems miles away as water and wind patterns shift. Some extraction is illegal. Sand mafias operate in India and other countries, stealing sand under cover of darkness. People have been killed protecting beaches from illegal mining. Sand has become valuable enough to fight over, profitable enough to steal, scarce enough to regulate. Scientists are searching for alternatives. Crushed recycled glass can replace some sand in concrete. Crushed rock from quarries works, but requires more energy to produce. Some researchers are developing sand-free concrete, though it's not yet practical for large-scale use. Better solutions involve using less sand, buildings designed to require less concrete, roads built with alternative materials, recycling concrete from demolished structures to extract the sand for reuse. These approaches work, but require changing how entire industries operate. The irony is painful. We live on a planet covered in sand, yet we're running short. The abundance we see in deserts and beaches is the wrong kind of abundance. The sand we need hides in rivers and coastal waters, and we're extracting it faster than Earth can make more. Future generations might look back and wonder how we let this happen, how we managed to create a shortage of something that seems infinite, how we forgot that even common materials are finite when consumption outpaces creation. Sand teaches us that abundance is not the same as endless supply. Sand is finite, but it's also ancient, resilient, and constantly transforming. We followed it from mountain peaks to ocean floors, from microscope slides to glowing beaches, from hourglasses to human bones. Now, let's return to where we started, to that single grain resting in your palm. You understand it differently now. That grain isn't just a speck of rock. It's a traveler that's been moving since before your species existed. It might have started as a mountain when dinosaurs walked the earth. It tumbled through rivers while ice ages came and went. It witnessed everything and remembers nothing, just keeps moving, keeps transforming, keeps being sand. The grain in your hand connects you to everything we've explored tonight. It contains silicon that's similar to the silicon in your bones. It might have been part of a parrotfish's meal before becoming beach sand. It could have glowed with bioluminescent life. It definitely filtered water at some point, cleaning it grain by grain. It sang songs in the desert or squeaked under footsteps. It measured time in an hourglass or became glass in a meteorite strike. Every grain carries these possibilities. The sand on every beach is a mixture of travelers from different places, different times, different origins. They arrived separately but rest together. Your footprints press them into temporary patterns. Waves rearrange them. Wind takes some away. New grains arrive. The beach is never the same twice, yet it's always recognizable as itself. This is what sand teaches us about permanence and change. Nothing stays the same. That mountain became pebbles, became sand. That sand might become sandstone, then erode back into sand again. The cycle continues forever, or near enough that the difference doesn't matter. What we call permanent is just slow change. What we call change is just patterns we can see. You're like sand in this way. The atoms in your body are temporary visitors. You replace them constantly through eating, drinking, breathing. The you from 7 years ago shares almost no atoms with the you right now. Yet, you're still you, continuous but changing, permanent but flowing, like a dune migrating across a desert, always moving but always itself. Sand also teaches abundance. 7 quintillion grains, more than stars in the universe, more than you could count in lifetimes. This abundance suggests that nature creates generously, that there's enough wonder to go around, that your share of beauty and mystery is guaranteed simply by being here. But sand's scarcity reminds us to pay attention. Even abundant things can become rare if we're careless. The sand we need is running low because we forgot that using something faster than it's created leads to shortage. The lesson applies beyond sand, to water, to forests, to time itself. So, hold that grain one more time. Feel its weight. Notice its texture. Remember that it's older than civilization and might outlast whatever comes after us. It's been everywhere and belongs nowhere. It's common as dirt, but unique in its details. It's simple, but contains multitudes. Let it go now. Put it back. It has places to be, journeys to continue, and you have rest to find. If tonight's journey brought you peace, please tap that like button and subscribe. We explore science for sleep every night, finding calm in the universe's quiet wonders. Leave a comment about your favorite sand fact or where you're watching from. This community grows grain by grain, like a beach building itself, one story at a time. Tomorrow, we'll explore something just as simple and just as infinite. Until then, rest easy, knowing you're made of stars and sand and everything in between. Sleep well